the production process. And fixing vulnerabilities and defects in the product, the cost for that actually changes from the independent stages of the product. So if you detect that very early on, before even checking the code, then it's more effective. You know, the developer can just, fix the bug, find the problem, fix the bug, and that's it. If the code is checked in, a large number of people are going to be affected by this, depending on the size of the group, depending on the, how many developers and testers and so on are going to be impacted by the same change. And if it's very difficult to find, those bugs, those defects can actually stay there for quite a long time. And once the product is shipped, the cost of fixing that thing is it's even more higher. So we want to set the trend in the industry for the Windows development that we have less tolerance to to poor quality of the code. We want to make sure the heap functions are properly used, the buffer are properly sized, and we want to make sure that we detect and we cache this as soon as possible. And we encourage anyone to enable the termination on error as appropriate. And furthermore, we expect that in time is going to reduce the compatibility impact we have today. Because as people develop more applications, starting with Windows Vista and so on, we expect to have less applications exposing heap overruns and double free and other errors that we used before, because they can see this in production in development phase. So now, if we look back, what we did in Windows Vista and what were the known attack vectors after Server 2003 and XP SP2. First, we removed the looker side list and the array of list entries that were the next low-hanging fruit that I heard of. Today, I'm not aware of any real exploit that was built on top of that. They were more like a proof of concepts, if I understood very well. But there were like some chances they may get some attention. We also have integrity check on block header, and this is a very good obstacle in brute force attacks, so we can detect this very early on. And we take the stand to terminate on errors much earlier, which was not the case before. And we also look at the heap changes. That they have a small common ground with previous heap management. So beside the variation on dynamic variation and the algorithms and so on, it's also the heap itself, the structure itself changed a lot. So this is a very interesting point for the portability of the exploits, because they need, in order to run on Windows Vista and also run on XP and Windows 2000 and so on, it needs to find that common ground, or it has to kind of handle differently the heap structures and how can it take advantage of that. And the security enhancement are just a journey. So we are going to improve as we learn about new exploits and new methods and so on. And most important is that application developers need to understand that the mitigations are not a substitute to the real fix. This is just like some barrier in the way of the exploit, but every single bug, every single security vulnerability needs to be fixed. And in Microsoft, we have this culture, and I hope everywhere in application developers the same thing. So now to show the security enhancement, let's see how we look from the performance and reliability perspective. And here we can see that we improved a lot of scenarios for multiprocessing and multi-core processing and multiprocessor scenarios. We addressed a lot of critical external fragmentation scenarios, and also we have a better scalability with large heaps. We improved the reference locality on 64-bit platform by default. It used to be this mostly on only on low fragmentation heaps, starting with Windows 2003 Service Pack 1. And we resolved problems that were exposing, exhausting the virtual address space. And also we increase resilience with some long-term mixture of long-term allocation with short-term allocations that may cause severe fragmentations. I'm going to show some graphics and some numbers on top on that. So the key enhancements were with automatic tuning. We have a very low granularity and tuning the heap algorithms and tuning the policies. And we have extensive use of lazy initializations to reduce the heap creation cost, which used to be a problem for low fragmentation heap in the earlier versions. And the most significantly was actually the entire segment management redesign. Currently, there is this exponential growth that, as mentioned before, is handled differently. There is an unlimited number of segments, which allows us to have a very good performance on a 64-bit platform, or 64-bit platform from now on, and how the application increase is going to be very, very well affected. And we have improved also internal lookups algorithms. Most of them are constant time algorithms when it used to be sometimes linear algorithms and so on. And you can see some numbers later how we address those numbers. So here is a benchmark, which is multi-threaded applications, which allocates concurrently for multiple threads, like random blocks in the range of 0 to 1K, and the second graph is from 4 to 8K. And you can see the blue line. I'm not sure you can read the letters here, the text there. The blue line is for the Windows Server 2003. And this is, and the red thing is Windows Vista. This was running on an 8-processor machine, 64-bit, 4 real processor dual core. And you can see in this range from 0 to 1K, the leukocytes were used before, and the performance was affected by the processor trashing the cache lane from one to each other. And you can see kind of a steady performance. Even if you have like 8 threads and 8 processor, you don't get too much of the throughput that you could in an ideal scenario. While in Windows Vista, we detect a lot of the contention of runtime, and we scale up very close to the ideal case, where we get a very high performance, such as almost close to 8x when you have running this on 8 processors. And this is not actually even the worst case. The worst case is actually when you don't even have random distribution of the blocks, is when you have one block size allocated from all these threads at the same time, because this actually increases the chances to trash the cache line from multiprocessors. And the graph in the Windows 2003 will be even worse than this. You would see a similar performance with low fragmentation heap Windows 2000. However, the application explicitly needs to initialize the low fragmentation heap, and it was a large footprint involved with this to begin with. And if we go to larger blocks where the leukocytes were not used, we see the numbers actually, the improvements are actually even much significant. And this is, the low contention, it's telling its word there, where you have significant, like an order of magnitudes difference in performance in the same scenario. Now, I mentioned there are some patterns with the segment management and the way we manage the blocks that some large applications were seeing. And you can see this is a pattern which exposes long-term allocation of 8 bytes. And you can see that in time, actually, the overall cost in address space was around like 4 or 5 kilobytes for every single 8 bytes usage. Yeah. And you can see that also commit size is around like 500 bytes for every block. And everything at a very high cost. If you look at the performance, the cost of having those allocations, of having the heap operations was very high when the heap was fragmented. And you can see like how the improvement also went in this area as well. Another way to look at this is like a different pattern that exposed fragmentation before. You can see kind of across the, in kind of broader, large of pattern usage, you can see like 7,000 times improvement in those scenarios. And obviously, this is not happening in every single application. This is not happening in every single server process. But this may be a part of like a fraction of the overall performance cost that some big applications or server were seeing. Just one more thing on this side that I want to notice. This is, just a test which allocates, 2 gigabytes of memory in different block size. So I would just like you to notice that the reserve size is having a spike from like 2 gig to 4 gig when a new segment was allocated before because of the exponential growth in segment size. And in Vista, we have the segment size, the virtual address tracking very well the commit size. So we are going to come to the end of the talk. So as a summary, the attacks get more sophisticated, but so the heap management. And it's not only for the security perspective, it's not only for the security, it's also for the performance. And we made a big step to lay down the foundation to increase our agility to respond to new exploits and respond to new way of people taking advantage of the heap structures. And also, we have a stand to reduce the risk of compatibility in the future. So we expect, like many years from now, the compatibility bag is going to be lower and lower. And at the same time, we had significant improvement in multiprocessing, in multi-core multiprocessing, and we handle better large fragmentation scenario, large heaps and fragmentation scenarios. And we are not yet done. So we are looking to innovate even further. So I'm looking for feedback for you guys, and my alias is adrmarine@microsoft.com, or you can send also mail to this alias, heapex@microsoft.com. And you can find the debug tools that I used in the demo at this link, and the application verify. I'm not sure you can remember the application verify link, but if you just search for on the download side, you can find this very quickly. So next, we're going to hear from Tony about the life cycle and Internet Explorer 7, and I can take a few questions, right? Okay, so I guess so. Thank you very much.